Hi, I'm Nico, and this will be a quick intro into Houdini RBD Bullet Solver. First, let's actually build something that we're gonna break. Create the geometry. Let's call this FX. We will put all our effects inside here, but I like to have a floor, so let's just quickly create a grid. And that's enough. Let's create a box. We will move as a relative channel here, so and multiply it by 0.5. So now whatever measure we have on the height, the box will lie completely on the ground. Let's give it 2 meters height, 2 meters in X, and only 0.1, so 10 centimeters. Now let's just do it 0.15 centimeters depth. So now we have a nice box that represents our wall. So let's start by fracturing this wall. For that we can use a Rbd Material Fracture, and we connect our box inside here. At first you may not see nothing because it's actually broken. If you activate the wireframe, you can see how it's actually broken in many pieces. They hide everything else, including the grid, and let's just focus on our wall for now. The Rbd Material Fracture will create points inside the volume of the area that you gave it, in this case the box, and apply the noise to it. But it cannot spread the points in an irregular fashion, and we want to break our wall in the middle, like an explosion from the center. So we kind of need to give the material fracture some points to tell them where exactly should the fracture happen. So for that, let's create a sphere. We have the sphere here. Let's see the wall in wireframe, so we know where to put it. Okay, let's add a transform. Let's move the sphere more or less to the center of the wall. It doesn't need to be exact at all. And let's give it a dimension. Yeah, actually, just move it exactly one. And let's do a dimension in C, 0.2. So it's relatively flat, and all the points that we create are gonna be inside the wall or close to it. So let's just scatter a bunch of points in that surface by just using the scatter. Now 1000 points is a lot, so let's just choose 100 points. That should be more than enough. And we add it to the last input of the material fracture node, which is in order to add extra points to the fracture. Once we do that, let it calculate. The material fracture has different settings, and right now we have 2 level of fracture, meaning that it fractures the wall that we created in one level, and then inside each of those pieces another level more. So in the first level, let's change the sparse convolution to just purling noise, and let's use input points, and now you will see how we're gonna have a lot more points in the middle. Now we don't waste a lot of memory and computational power, because we will be focusing exactly in destroying the center area while keeping the large pieces intact. We enable chipping, and it will create small little chips in the edges of the destruction. It's not very visible just from the wireframe, so what we can use is Rbd Exploded View. This actually shows then all the pieces exploded. You can also use it with another node called Exploded View, but the benefits of the Rbd Exploded View is that you can actually use it to show the constraint. But let's try it by running the simulation as we have it right now. So let's just drop an Rbd Bullet Solver and connect the first input, the geometry, to the geometry, and the proxy geometry to the third input. Now, I have a long play timeline. Let's reduce it to 100 frames, should be more than enough. You know what, in order for speed, let's just keep it at 50 frames actually. And let's see what we get. Everything falls. We don't have any ground, but the gravity works. So let's add the ground. Inside the Rbd Bullet Solver, there is underground. You can add the ground plane. Now, since I don't really like to see my ground, I can go to visualize and turn off display visualization geometry, and that's it. For now, this should work perfectly, and now we have a ground where all our pieces will fall. But this is pretty boring, right? I mean, we just have the wall just crumble upon itself. Let's try to improve this by adding an explosion. But before we add our explosion velocities, what about we improve a little bit how our fracture actually looks like? Right now it's a little bit too simple. Let's see it in the wireframe mode, and I would like to have some more details. In our secondary fracture, let's change the sparse convolution to original parallel noise. Yeah, that looks a lot better. That's a lot of pieces, and it's going to be rather interesting once that it explodes. Now we need to define which pieces are actually not going to be active. That actually will be the best way to keep them in place as the rest explodes. We can do that really easy with Rbd configure. We just connect it. We don't need the Rbd explode anymore. In the Rbd configure, we can select, just by selecting the points, all the pieces that we don't want them to move. So basically they're just freezing time. That should be fine. Select those, and then we set them to inactive. That means that they will never move. Let's run the simulation now and see what we get. Okay, we're getting something here, but it's still pretty boring. It's just the wall just crumbling in the area that we decided will be active. We can do better than this. Like I said, let's add velocity so there is an explosion here. Let's create a group first, where we're gonna get all our proxy geometry into it, and I'm just going to copy the group that we decided before, all these points, come here, paste it here, and it selects the same points, but we want the inverse actually. So I'm just going to go here and then inverse selection. Now we have all the points that we didn't select before. Press enter. And now we have selected the points in the middle, the one that we didn't select here. Perfect. So all these are active. Now I want to add velocity to them. Right now my group is called group 1. I have it here set up to be my node name, but you can just actually call it group 1. Now with point velocities, we can add velocity to this. We select the group 1, and I will add velocity to all this with the conical noise. But there's a problem. I don't see anything on the screen. How do I know where the velocities are going? Where exactly are going to explode? In which direction? Well, for that you're using Houdini something that is called visualizer. You can click on the eye. It gives you a lot of information about the current geometry, and somewhere in there, very difficult to see in this small screen, but there we go. And now we see the velocities. If you wonder, this is with the visualization here. You can deactivate the visualizer or not, or deactivate it here. Right now they're all going upwards with a certain cone angle of 30 degrees. I don't like that direction. I want it to go on the z-axis. And cone angle 30 degrees is fine, but it's still, let's put the cone angle at 1. It's still pretty boring. They all have the same velocity outwards, no gradation whatsoever. So we can do a little bit better than that. For that we're gonna do a quick point wrangle. Let's start by creating a sphere. This is going to be just a primitive. I'm gonna use this sphere only to measure the distance from the pieces to this sphere, and whatever is close to the sphere is going to go out of the wall a lot more quicker. Let's move the sphere maybe, yeah, 1. So it's exactly in the center of the wall. So everything close to the sphere is going to go outwards of the wall a lot more quicker. How we do that? We start with the point wrangle. Let's add the point wrangle. Let's connect or point velocities in the first input or spheres in the second input. In the wrangle, let's add this expression. It's relatively simple. Let's create a float that we'll call it this, which will be equal to the distance between which points? Our current point position, which is represented by @p, and the position of our sphere. Our sphere comes in our second input, so that will be 0, 1. So let's call it point 1. Which variable we want to call? The position. And which point it is? Well, we only have one point, so that will be point 0. So now we have the distance. Now what we do with this distance? Let's expand this a little bit more. We're going to multiply our velocity. So this multiply equal to our distance, but we don't want the distance to be exactly the multiplication. We want to transform the distance. It goes from 0, which is the closest position to the sphere that we have, from 0 to 1, to go from 1 to 0, right? Okay, let's do that. Our distance, it will fit the value between 0, and this is trial and error, but I will decide 0.35 meters. It will go from to 1 until 0. Let's see what we get as a result. And now we see the velocities, as they're close to the sphere, are a lot more larger, the values, than as they go far away. Why? Because as the distance increases, we're formatting the distance from 0 to 0.35 meters to 1 at the center to 0 at the edges. That's more interesting, right? Now let's go back to our velocity and let's increase the angle. 30 degrees is 0 degrees will be too boring. Let's add it like that for some randomness. Let's connect those velocities that we had into our proxy geometry and let's see what we have. For that, remember to turn off the velocity visualization. So we can see that it's still pretty boring because the velocities are pretty low. So let's give it more velocity. Let's scale this to 5 and see what we get with that. Okay, this is a lot more interesting now. We have a wall and there is a little explosion that pushes the pieces outside of the wall. Now, we have a bunch of pieces that they continue to roll around and go crazy in particular. I don't really like that, so I'm gonna teach you a quick pop wrangle inside the sim that we can add in order to slow down to a halt anything that starts moving slow but still continue rotating or moving in the ground. For that, we go inside the Rbd bullet solver. Inside here, we can add our own forces or wrangle in the pre-solve. We're gonna add a pop wrangle connected to the pre-solve. Let's go back to frame 1. And in this pop wrangle, we're gonna calculate first the speed, which will be equal to the length of the velocity. I also want to copy this and calculate now the speed of the rotation. That's represented by W, so that will be equal to the length of the rotation velocity. Now, I will make a quick if statement. Then if the speed is under, let's say 1, let's be a little bit extreme, then I will multiply the velocity by 0.9. I'm going to go a little bit extreme. I want to do the same for my speed of the rotation, speed W. If it is under 1, let's multiply by 0.9. Now, let's see what we get from there. Okay, now that looks a lot better. The pieces, once that they hit the ground, they start slowing down and they go to a halt. Looks a lot more realistic in my opinion. So let's stop a second for here, but let's add a little bit more oomph to our explosion. Let's add more velocity. Keep it to 15 and let's turn off the wireframe. And let's see what we get. Now that is a wall being destroyed. And that's it for today. I hope you guys enjoyed this Houdini tutorial. Of course, there's a lot more to unpack into the bullet solver and RBDs in general, but I hope this was a good intro into the RBD bullet solver. See you next time.